I got my pen working great. Okay, guys, so we're going to go over another application of integrals. We're going to talk about the fact that an integral can help you calculate an area. Now, we already know that an integral is, in fact, an area under a curve. But if we had, for example, two curves, okay, try drawing a better picture. Two curves. I should have made a graph on Desmos or something. And one of our functions we'll call f. And one of our functions we'll call g. Maybe g is kind of parabola-ish. So there's g. And maybe there's a section between f and g that we want to find the area of. Okay, maybe from this point to this point. That kind of makes a boundary. So we've got this kind of curvy part at the top. We've got sort of curvy part at the bottom. We've got these sides for boundaries. We're going to call those boundaries A and B. And if I want to calculate the area sandwiched between two curves for a region where the f function, or one of the functions, is always above the other. So we have a top function and we have a bottom function. If you kind of imagine yourself standing, oops, I have a little eraser here, make a little space for you, okay. So imagine yourself standing in here, and you've got one function above your head and one function below your head, and you're trying to find the area around you. That area is going to be found by looking at that integral. We have a left boundary, that's A. We have a right boundary, that's B. So A is the boundary on the left, B is the boundary on the right. Sometimes those are given to us. Sometimes they happen kind of naturally because of intersections. We'll look at a couple different versions. We have a top and a bottom, and a left and a right. And if we calculate the integral from A to B, from left to right, of the top function minus the bottom function, that will give us that area. And so not just an area between a curve and an x-axis, which is one thing an integral does. Okay. We can do an area kind of anywhere. Anywhere we can sandwich it, or imagine sandwiching between two curves as boundaries and having, oops, I have to do those in red, left and right boundaries too. All right, so we're going to look at a couple examples of this together, two slightly different approaches, or two different sort of scenarios. What we will be doing, at least first, is we're not going to use any u substitutions. We're not going to need those. We're going to stick with kind of nice functions. And eventually we're going to, if we get to some little messier functions and we still want to find areas, we're going to look at how the technology can do a lot of the work for us. So in problem 1, I have a graph already for you. One of your curves is x squared plus x plus 2. Okay. The other one is y equals negative x. Now, we could graph these on our calculator to verify. I'm hoping what you would think about and know is that something that's x squared plus x plus 2, the x squared, that would make it kind of curvy, where y equals x is just a nice, or actually y equals negative x, negative slope line going through the origin. So we have a top and a bottom. And we're also given two more pieces of information to create our left and our right boundary. X equals 0 is our left boundary. So we'll draw a vertical line to represent x equaling to 0. We'll draw a vertical line at 1 to represent x equaling 1. And so there's my area. And if we make a little space for you in there, oops, there you are, there you are. The red function, the quadratic, is on the top, and the linear function, the green guy, he's on the bottom. So take a minute and see if you can write me the integral that will calculate that area, the area between x squared plus x plus 2 and y equals negative x. All right, hopefully this is what you're thinking. I'm in my classroom and we got, oh, plus, got a bunch of suns shining right on my thing here. Minus negative x dx. Okay. Always top minus bottom. Always a minus in there. Okay. Now, how are we going to calculate this? Well, if we're going to go by hand, we would have to simplify, or we could simplify, it would make it easier. And so I would say 0 to 1, x squared plus x plus 2 plus another x. Let's see if I can get another page in here. All right, so if we're looking at 0 to 2, x squared plus x plus 2 plus another x, we might combine some terms. So the x and the x makes a 2x. And since I don't have anything inside of parentheses raised to a power, I don't have any quotients, I don't have any e's, I don't have anything that's going to require a u substitution, I can go backward power rule to find big F. So x cubed over 3 from the x squared plus 2x squared over 2 plus 2x. So if I do big F of 2 minus big F of 0, that's going to be an 8 over 3 plus an 8 over 2 plus a 4, when I plug a 2 in there, minus what's going to end up being a bunch of zeros, and this is an 8/3, and this is a 4, and this is a 4. So if we add all that together, and maybe you flip it into a fraction, we're going to get something like 10 2/3 or 32/3. Something doesn't seem right. I wonder if I did something wrong on my key before. This is how you know it's me really doing the video, because now I'm questioning my work like I always do in class. Hang on a second. Let's double check. You guys aren't here to tell me what I did wrong. If I did something wrong. X squared x 2. So x squared. No, I think I did it right. Actually going to show you something here in a minute that's going to help you with that. So let's see. X squared 2 minus x. Yeah, that's right. Must have done something wrong before when I wrote it on my notes. All right. So, it's an integral problem to calculate an area. That's not new. The new part is writing your own integral. Okay. Now, in problem number 2, once again, I have a graph for you. This time, this guy, 6 minus x squared, appears to be the top, and y minus x, oops, still blue, or y equals x appears to be the bottom, because if we were standing in there, standing on the x-axis, or standing so that we were standing straight like the y-axis, 6 minus x squared would be above our head. In this problem, we're not given any boundaries for left and right because they happen kind of naturally. Since we weren't given any specific boundaries, we have to go with, well, what boundaries might already be there? If I look at 6 minus x squared and I look at y equals x, they intersect. They cross at -3, and they cross at 2. And so the integral, to get my area, is going to be the integral from -3 to 2 of 6 minus x squared minus x dx. Once you write the integral, really the new part of the lesson is over. The rest of the problem, coming up with the antiderivative, the big F, and doing all the arithmetic work, that's all old news. The new part is the top minus the bottom, left boundary, right boundary. Now, I will write out all the work for this. I don't think you need to watch me write it all out. I'm going to also show you another kind of trick here. But this guy's going to come out to be 1/25/6. Okay. I'm going to go ahead and stop this first video so one video doesn't get too long, and in the second video we're going to look at a couple of the problems on the back, and we're going to look at how our technology can help us with this a little bit more than you may have known. So stay tuned.